All right, continuing with our physics topics and formula sheets, angular momentum and torque. I just put a table with some of the units in linear terms and angular terms at the top, so you can take a look at that. So right here, I just defined what a radian is. So in angular velocities and angular momentums, we're going to be measuring instead, like what we did with linear, we measured in meters per second. Velocity was measured in meters per second. So we talked about the traversing of meters in the linear, and now we're going to talk about the traversing of radians. So if you think about this, where this is the radius and s is the arc length of this segment, where this segment, this theta, is equal to 1 radian when the arc length is equal to the radius. So if you have the arc length, which is this, equal to the radius, which is this, the angle that you get here is 1 radian. Well, there happens to be 1, 2, 3, 4, 5, 6.28 radians in one circle, or look at that, 2 pi radians. All right, so 1 revolution is equal to 2 pi radians, and then omega is radians per second. So linear is measuring things in meters per second. Angular is measuring in radians per second. So how many turns per second, that sort of thing. RPM, radians per minute, or revolutions per minute, that sort of thing. Okay, torque is equal to force times lever arm distance. Well, fulcrum is the point of rotation, so then the lever arm distance will be determined by the distance from where the force is applied from the point of rotation. So the point of rotation in this case is at 5. The force, mg, is at 1, so it's 4 units from. Okay, and then we have this other mass, which is at 7, so it's 2 units from the point of rotation. So in order for this system to be balanced, we've got to consider the clockwise torque must equal the counterclockwise torque. So remember we talked about forces, force left minus force right, force up minus force down. Well, this is torque. Torque clockwise minus torque counterclockwise will give you the net torque. So let's consider this. A board is hanging from 2 cables, and there are 2 points of support, A and B. So if one of these is cut, what will happen? Well, let's leave A stationary and cut B. Well, the board's going to rotate clockwise. That means the force at B is providing counterclockwise torque. Same kind of thing happens here if you have like a cantilever or a diving board. So you have 2 points of support, A and B, and then you have a diver out on the end. Well, the center of mass of the board is located some point past the point of rotation. If you let B be the point of rotation, you could also let A be the point of rotation. Doesn't matter. Choose one. And then you're going to calculate based on what's out there, what's causing the torques. The diver and the center of mass are both causing clockwise torques. Then if you let B be the other force being applied and let A be the point of rotation, then B, the force at B, is providing a counterclockwise torque. Same kind of thing can be summed up in this little diagram here. So you have lever arm distances 1, 2, and 3 that are all equal. Force 1 is equal to force 2. They're in opposite direction. Oh, those work together. So force 1 times lever arm distance plus force 2 times lever arm distance 2 are both rotating it counterclockwise. Well, this force is 2 times those forces in the same lever arm distance. So this system would be balanced. Okay, so let me flip this over. I have some more things to talk about. Angular momentum, linear kinetic energy is, I'm going all over the place. So let's talk angular momentum in a moment. Linear kinetic energy is 1/2 mv squared. Angular rotational kinetic energy is 1/2 I omega squared. So in that case, we need to know what I is. So I, for different shapes and orientations, I'll give you that sheet later, but I is typically mr squared. So if you have no rotational inertia given, use mr squared. That's the same as it is for a mass on a string, like a pendulum. Okay, so conservation of energy and momentum. Linear momentum is mv, angular momentum L equals I omega. So here's the comparisons of the linear and the angular equations, including Newton's second law, F equals ma. The angular version of that, instead of force, it would be torque. M would be substituted with I, and acceleration A would be substituted with alpha. There you go.